You hear the words quantum computing and artificial intelligence, and your brain might shut down. Too complex, too future, too sci-fi. But while you were scrolling, something happened in labs across 3 continents that changed the game forever. December 9th, 2024, Google unveils Willow, a quantum chip with 105 qubits that solved a problem in under 5 minutes. The same problem would take the fastest supercomputer on Earth 10 septillion years. That is 10 followed by 25 zeros. 10 million trillion years. The universe is only 14 billion years old. Willow finished before your coffee got cold. But here is what nobody is telling you. This is not just about speed. 7 quantum breakthroughs are stacking right now that will create AI so powerful it will not compute like us. It will compute like nature itself. Parallel, probabilistic, conscious. And you will see it in your lifetime. Achieving 13,000 times speed up over classical supercomputers, and IBM's November 12th, 2025 press release detailing their quantum Nighthawk processor with 120 qubits and 218 tunable couplers demonstrating fault-tolerant error correction. These are not press kits. These are peer-reviewed breakthroughs from labs with cryostats, cooling chips to 15 millikelvin. Now back to the information. The idea that you could add qubits and errors would drop instead of rise. Theory said it was possible. Hardware said otherwise. The math worked on paper. Quantum error correction codes existed since Peter Shor published his breakthrough in 1995. Surface codes, toric codes, concatenated codes, all elegant on blackboards, all brutal in silicon. The problem was physical. Qubits are fragile. They exchange information with their environment constantly. Decoherence. The quantum state collapses. Information lost. You need redundancy. Encode one logical qubit using many physical qubits. But every physical qubit you add brings its own errors. More qubits means more noise. Classical error correction works differently. Copy bits, check for flips, correct, simple. Quantum mechanics forbids copying. No cloning theorem. You cannot duplicate an unknown quantum state. So you cannot just make backups and vote. You need entanglement. Measure syndromes without measuring the qubits directly. Infer errors from correlations. Correct without collapsing the computation. Researchers built small error-corrected qubits. 3 physical qubits protecting 1 logical qubit, 5 qubits, 7 qubits. But the error rate of the logical qubit stayed the same or got worse than a single physical qubit. The overhead was too high, the gates too noisy, the measurements too destructive. Crossing threshold meant proving you could scale, add physical qubits to a logical qubit, and watch the logical error rate drop. Exponentially, not linearly, exponentially. Willow changed that in December 2024. Google Quantum AI in Santa Barbara ran tests on qubit grids, 3x3, then 5x5, then 7x7. Each time they doubled the grid size, the error rate cut in half. Exponential reduction. The holy grail. The specific numbers matter. Distance 3 surface code used 9 physical qubits in a 3x3 grid. Logical error rate measured at 10 to the negative 3 per cycle. Distance 5 used 25 physical qubits. 5x5 grid. Logical error rate dropped to 5 times 10 to the negative 4 per cycle. Factor of 2 improvement. Distance 7 used 49 physical qubits. 7x7 grid. Logical error rate fell to 2.5 times 10 to the negative 4 per cycle. Another factor of 2. The pattern held. Each distance increase cut errors in half. This is below threshold. This is the exponential suppression that theory predicted. Hartmut Neven, founder of Google Quantum AI, called it an unfakeable sign. You cannot cheat exponential curves. The chip uses surface code error correction. Physical qubits group into logical qubits. When one fails, the group compensates. Willow hit coherence times of 100 microseconds per qubit, 5 times longer than Google's Sycamore chip from 2019. Gate fidelities reached 99.97% for single qubit gates and 99.88% for 2-qubit entangling gates. Readout fidelity hit 99.5% across all 105 qubits. These are not lab numbers. These are production metrics from a chip fabricated end-to-end in Google's Santa Barbara cleanroom. The facility went live in 2023. Before that, Google shared university fabs. Turnaround time for a new chip design was months, now it is weeks. Anthony Migrant, chief architect at Google Quantum AI, said vertical integration was the unlock. Materials to cryogenics under one roof. Every operation co-optimized, no bottlenecks. The result is a chip that does not just work. It improves as it grows. IBM followed with Quantum Loon in November 2025, an experimental processor demonstrating all hardware elements needed for fault tolerance. Loon introduces multiple high-quality, low-loss routing layers, physical connections called C-couplers that link distant qubits on the same chip, not just nearest neighbors, long-range entanglement. The chip also features qubit reset technology. Between computations, qubits flush their state. No residual errors carry forward. Clean slate every cycle. Julian Kelly, director of quantum hardware at Google, said error correction is the endgame. Willow is not a demo. It is the architecture for scaling. By late 2025, IBM shipped Quantum Nighthawk, 120 qubits with 218 next-generation tunable couplers in a square lattice. Connectivity jumped 20% over IBM Heron. Circuit complexity increased 30% while error rates stayed low. Users can run up to 5,000 2-qubit gates, the fundamental entangling operations that build quantum algorithms. Nighthawk launched to IBM Cloud users by December 2025. Real-time access, no waiting list. Researchers at HSBC used IBM Heron in September 2024 to improve bond trading predictions by 34% versus classical methods alone. Quantifiable advantage. Error correction also unlocked real-time decoding. IBM proved in November 2025 that classical hardware can decode quantum errors in under 480 nanoseconds using QLDPC codes, quantum low-density parity check codes, faster than the quantum operations themselves. You can catch errors before they cascade. This is the shift. Quantum computers are no longer fragile lab experiments that collapse if you sneeze nearby. They are becoming robust systems that heal themselves faster than they break. The threshold is crossed. Scaling begins. Formerly, the out-of-order time correlator. OTOC, it measures how disturbances spread through quantum systems, molecules, magnets, materials, even black holes in theory. On Willow, quantum echoes ran 13,000 times faster than the best classical algorithm on one of the world's fastest supercomputers. 13,000x, not 10% faster, not twice as fast, 13,000 times. The algorithm works like this. Send a signal into the quantum system, perturb one qubit, reverse the signal evolution, listen for the echo. Quantum interference amplifies the echo. Constructive interference. Waves add up. Signal gets stronger. You measure with extreme sensitivity. The application is a molecular ruler. Quantum echoes extends the reach of nuclear magnetic resonance spectroscopy. NMR. Traditional NMR measures distances between atoms and molecules. Critical for drug discovery, understanding how medicines bind to targets. But NMR has limits. It cannot see far. Quantum echoes pushes past that wall. Google partnered with the University of California, Berkeley. They tested two molecules, one with 15 atoms, another with 28 atoms. Willow computed molecular geometry. Results matched traditional NMR, but the quantum method revealed information not usually available, longer distances, hidden structures. Ashaka Joy, assistant professor of chemistry at UC Berkeley and collaborator with Google Quantum AI, said this is a molecular ruler that measures longer than today's methods. The implications hit drug discovery first. Pharmaceutical companies spend years mapping how drug candidates interact with protein targets. Quantum-enhanced NMR collapses that timeline. Materials science follows. Polymers, battery components, superconductors. Even the materials that make qubits themselves. You can characterize molecular structures that classical tools cannot resolve. Michel Devoret, chief scientist at Google Quantum AI and 2024 Nobel laureate in physics, called it a new step towards full-scale quantum computation. The breakthrough is verifiable. Independent labs can check the results. Classical supercomputers can verify the output even if they cannot match the speed. No more quantum supremacy debates where critics claim classical algorithms could catch up. Quantum Echoes delivers measurable scientific value, the first time in history. Another quantum advantage emerged in April 2025 from Hefei, China. Origin Wukong became the first quantum computer to fine-tune a billion-parameter AI model. Not simulate, not approximate, actually train. The Wukong chip has 72 computational qubits and 126 coupler qubits, superconducting. The team partnered with the Institute of Artificial Intelligence at Hefei Comprehensive National Science Center. They took a large language model, 1 billion parameters, fine-tuned it using quantum computing. The method converts model weights into a hybrid system, quantum neural networks plus classical tensor networks. Dayu Mengen, vice president of Origin Quantum, said the quantum engine works with the classical model. They collaborate. Quantum explores vast parameter combinations simultaneously through superposition and entanglement. Classical methods like low-rank fine-tuning hit bottlenecks, limited generalization. Quantum sidesteps that. Chen Zhaoyun, associate research fellow at the Institute of Artificial Intelligence, called it the first real-world large model task on quantum computing. Existing hardware can preliminarily support large model fine-tuning. Since launch in 2024, Origin Wukong completed approximately 350,000 quantum computing tasks for users from 139 countries. Applications span fluid dynamics, finance, biomedicine. The world's largest scale quantum computing fluid dynamics simulation ran on Wukong. Financial quantum cloud experimental platform integration tested more efficient problem solving in the finance domain. Quantum advantage is no longer theoretical, it is operational. Molecules measured, AI models trained, industries transforming. Quantum entanglement without entanglement that rewrites network rules. December 7th, 2024. An international team led by Nanjing University and the Max Planck Institute for the Science of Light published a discovery that flipped quantum networking on its head. They found a simpler way to create quantum entanglement between distant photons. No pre-entangled pairs, no Bell state measurements, no detecting all auxiliary photons. Just the indistinguishability of photon paths. For over 25 years, entanglement swapping was the workhorse protocol. You start with two entangled pairs, perform a Bell state measurement, entanglement transfers, but it is complex, expensive, error-prone. The new method uses quantum uncertainty, make all possible photon generation paths identical, erase the clues to their origins. Entanglement emerges from not knowing which source produced which photon. Mario Kren at the Max Planck Institute for the Science of Light led the research. His team built an AI tool called Pythias, initially tasked with rediscovering standard protocols. But Pythias kept suggesting a simpler approach. Too simple. Kren and his team tested it anyway. It worked, published in Physical Review letters. The experiment generated photons from multiple sources, adjusted the sources so outputs became indistinguishable, detected photons at certain paths. Two other photons that never directly interacted emerged entangled. Pure quantum uncertainty. No prior entanglement source required, no measurement apparatus. Kren wrote on social media that this changed his perspective on what is necessary to create entanglement, not because we now know what is necessary, because we realized what is not. The breakthrough simplifies quantum networks. Links between distant locations become easier to construct. Multi-node networks scale better, less complexity, fewer failure points. Quantum communication and quantum internet benefit immediately. Secure message transmission. Distributed quantum computing. Networks that were impractical become feasible. Scaling to practical network sizes still faces challenges. Environmental noise, device imperfections. But the principle is proven. AI-assisted discovery. Pythias found a solution humans overlooked for decades. December 11th, 2024. Researchers used AI again, this time to streamline quantum entanglement detection. Neural networks measuring entanglement in equilibrium and non-equilibrium states. Published in NPJ Quantum Information on February 20th, 2025, the protocol uses machine learning to detect entanglement from local measurements. No full-state tomography. Exponential measurement scaling avoided. Entanglement quantification, logarithmic negativity, parity transpose moments, measured accurately. The method predicts long-time entanglement dynamics beyond measurement windows. Non-equilibrium quantum simulations often require long-time evolution. But current quantum devices have limited coherence times. Neural networks trained on short-time data extrapolate to future states, tested on ground states and dynamical states of local Hamiltonians. Success. AI is not just using quantum. Quantum is teaching AI new tricks. Entanglement became a communication method in December 25th, 2025. Virginia Tech researchers developed EQ-MARL, entangled quantum multi-agent reinforcement learning. Machines coordinate without transmitting messages. Each agent gets entangled qubits. When one agent interacts with its environment, it modifies its qubit. Entanglement means changes appear in qubits held by other agents, no signal sent, just shared quantum state. Alexander Dario, PhD student at Virginia Tech, said we exploit the fact that doing something to one half of the qubit pair does something to the other. We do not care what it does, just that change happens. Tested against classical AI and non-entangled quantum baselines. EQ-MARL 1, especially in scenarios with limited or unreliable communication. Applications include drone swarms fighting wildfires, robots searching collapsed buildings, autonomous systems in signal-lost environments. Dario estimates real-world deployment in 10 to 15 years. Quantum hardware needs to get smaller and more robust, but the math works. The framework is proven. Entanglement is no longer just a physics curiosity. It is infrastructure. A researcher at Charles Sturt University in Australia published a neural network that uses quantum tunneling as its activation function, not inspired by quantum mechanics, actually using the physical effect. Quantum tunneling is when particles pass through barriers they should not be able to cross. Discovered in the 1920s. Explained radioactive decay, nuclear fusion in stars, scanning tunneling microscopes. Now it is inside AI. Ivan Maximov designed QT-DNN, quantum tunneling deep neural network. He trained it to recognize optical illusions. The Necker cube, Rubin's vase. Humans see these illusions and perceptions flip. Front face becomes back face. Vase becomes two faces. QT-DNN replicates that. Traditional neural networks with ReLU activation struggle. They do not switch interpretations like humans. QT-DNN does. It oscillates between interpretations, produces ambiguous results between certain outputs, just like human brains holding both interpretations before settling. Published in APL Machine Learning. The network is small, outperforms much larger conventional networks used in computer vision. Maximoff suggested hardware implementation using quantum tunneling diodes. Neuromorphic chips, low power, energy efficient, suitable for autonomous vehicles, conscious robots. The connection to cognition runs deep. Research suggests quantum effects may play a role in human perception and decision-making, not necessarily in the brain itself, but quantum mechanics models human thinking better than classical probability. January 14th, 2025. Follow-up research published in Big Data and Cognitive Computing. Maximoff and Maximovich tested QTNNs on image classification, emulating human perception and judgment. Quantum cognition theory applied. Results showed QTNN can replicate human-like decision-making. Compelling evidence. The network trained up to 50 times faster than classical counterparts. 50x speedup, less data required, better generalization. June 26, 2024, Maximoff published the theoretical foundation in Arcus. Quantum tunneling enables AI to recognize complex visual effects, fine arts, cinematography, deepfakes, fake news. Understanding how brains process illusions and build reality models becomes critical. Maximoff is exploring quantum effects in social behavior, radicalization of opinions in social networks, quantum-powered AI contributing to conscious robot development. The code is public. GitHub repository Deep Tunnel. Anyone can replicate. Hardware implementations are next. Quantum tunneling diodes already exist. Resonant tunneling diodes. Tunnel FETs. Fabrication is established. Neuromorphic quantum chips could arrive within 5 years. Another tunneling breakthrough came from adiabatic quantum computing. June 21st, 2024. Frontiers in Artificial Intelligence published research on training neural networks using adiabatic quantum evolution. Universal AQC method. Runs on gate quantum computers, broader range of Hamiltonians, more expressive neural networks. Previous work showed quantum annealing can train networks optimally and quickly using quantum tunneling, but restricted to transverse Ising models. Loss functions limited to quadratic binary variables. The new approach breaks that restriction, complex loss functions, non-binary parameters, real-world machine learning applications. Quantum tunneling lets the system escape local minima. Classical optimization gets stuck. Gradient descent hits a wall. Quantum tunneling goes through the wall, finds global optima. This is how nature solves optimization problems. Proteins fold, molecules form. Quantum mechanics explores solution spaces. Classical physics cannot. AI is learning to think like physics. September 2025. Harvard physicists demonstrated a coherent quantum system with more than 3,000 qubits. Published in Nature on November 17, 2025. Not just 3,000 physical qubits. Logical qubits with error correction. The system combines physical entanglement, logical magic, and entropy removal. Quantum teleportation transfers quantum states between particles without physical contact. Dolev Blivstein, lead author and now assistant professor at Caltech, said this is the first architecture that is conceptually scalable. It will take effort and technical development, but we can build fault-tolerant quantum computers. The system uses atoms trapped by lasers, neutral atoms, different platform than superconducting circuits. Ion-trapped quantum computers from IonQ and others also scale differently. Photonic qubits from PsiQuantum and Xanadu offer room temperature operation. Each platform has trade-offs. Superconducting qubits need cryogenic cooling, near absolute zero, 15 millikelvin, but they have fast gate times and mature fabrication. Trapped ions have long coherence times, low error rates, but slower gates and harder to scale. Photonic qubits work at room temperature, easy to network, but hard to create strong interactions for 2-qubit gates. Neutral atoms sit in the middle, reasonable coherence, scalable trapping. Harvard's 3,000 qubit system used Rydberg atoms, highly excited states, strong interactions, reconfigurable geometry. The collaboration included MIT, Marcus Greiner, George Vasmer Leverett Professor of Physics at Harvard, Vladan Vuletic, Lester Wolf Professor of Physics at MIT. Multi-institution effort. The achievement proves quantum systems can scale beyond the noise threshold, add qubits, and keep errors under control, not just in theory, in hardware, running complex circuits with dozens of error correction layers. IBM Condor reached 1,121 qubits in 2024, largest quantum processor built to date. Integrated into IBM Quantum System 2, modular design supports even larger processors. The roadmap extends to 2033, quantum computers executing 1 billion gates on 2,000 qubits. Integration with classical high-performance computing and AI accelerators, hybrid computational ecosystems. The quantum decade is here, not 20 years away. Not a future dream, hardware shipping, users accessing, problem solving. 13,000 times faster molecular computation that opens the quantum scope. We covered quantum echoes in number 2, but the magnitude deserves its own entry. October 22nd, 2025. Google Quantum AI published in Nature, the first algorithm running on quantum hardware that delivers verifiable advantage over classical supercomputers. 13,000x speedup. Not an estimate, a measured result. Benchmarked against state-of-the-art classical algorithms running on Frontier, one of the world's fastest supercomputers. Located at Oak Ridge National Laboratory, 1.1 exaflops peak performance, over 9,000 AMD EPYC processors, over 37,000 AMD Radeon GPUs, classical computing at its absolute peak. Quantum still won by 13,000 times. The algorithm computes the structure of molecules. 15 atom molecule, 28 atom molecule, verified against traditional NMR, matched. But quantum revealed information NMR cannot see. Distance measurements between nuclei, coupling strengths, relaxation times, structural details invisible to classical probes. Nuclear magnetic resonance spectroscopy has been the gold standard for molecular structure since the 1940s. Felix Bloss and Edward Purcell won the Nobel Prize in 1952. The technique uses magnetic fields and radio waves. Nuclei with spin absorb energy at specific frequencies. Resonance. Different atoms resonate at different frequencies. Chemical shift. The environment around each nucleus affects its frequency. Nearby electrons shield the magnetic field. You can identify functional groups, map molecular structure, determine three-dimensional geometry. But NMR has limits. Sensitivity decreases with distance. Couplings between distant nuclei are weak, hard to measure. Long-range structural information is missing. Drug molecules often have complex three-dimensional shapes, active sites separated by nanometers. Traditional NMR cannot resolve the full structure. You need X-ray crystallography, cryo-electron microscopy, other techniques, each with limitations. Crystals required for X-ray, freezing for cryo-EM, artifacts, uncertainties. Quantum Echoes pushes past that wall. The out-of-order time correlator measures how quantum information spreads. Scrambling. A local perturbation at 1 qubit propagates through the system. Entanglement distributes the information. Eventually, every qubit carries a piece. The echo technique reverses time evolution, runs the system backward. If scrambling was perfect, the echo vanishes. If scrambling was incomplete, signal remains. By measuring the echo strength at different times and different initial perturbations, you map the scrambling dynamics. This maps directly to molecular structure. Atoms in a molecule are quantum systems. Nuclear spins couple through bonds, through space. Perturbations propagate. Measuring scrambling reveals coupling topology. Which atoms interact, how strongly, over what distances. This is not incremental. This is a telescope moment. Microscope moment. Quantum scope. Seeing what was invisible. Drug discovery transforms. Protein folding. Enzyme mechanisms. Molecular binding. All become tractable. Materials science leaps. Superconductors. Catalysts. Polymers. Batteries. Designed from first principles instead of trial and error. The algorithm relies on Willow's performance. 99.97% single qubit gate fidelity. 99.88% 2-qubit gate fidelity, 99.5% readout fidelity, across 105 qubits, operating at scale, high volume of quantum measurements, large set of quantum gates, signal extracted from noise, precision matters. Willow delivers. The Quantum Echoes technique is a 4-step process. Run operations forward on the qubit array. Perturb 1 qubit, run operations backward. Measure the result. Signal overlap reveals how disturbance spreads, constructive interference amplifies. You detect quantum dynamics invisible to classical probes. Vadim Smilyansky, director of quantum pathfinding at Google Quantum AI, co-authored the paper. He said this is the first time in history any quantum computer successfully ran a verifiable algorithm surpassing supercomputers. First time. History. Verifiable. Not debatable. Not contested. Confirmed. The pharmaceutical industry is paying attention. Billion-dollar drugs take a decade to develop. Most candidates fail in clinical trials. Better molecular understanding shortens timelines, saves lives, cuts costs. McKinsey projected quantum computing industry worth $28 billion to $72 billion by 2035. Conservative estimate could be higher. Quantum Echoes alone justifies billions in investment. Universities are ramping up. MIT Center for Quantum Engineering, Stanford Q-Farm Initiative, Quantum Information and Computation Center. Training the workforce, building the tools, publishing the breakthroughs. This is not hype. This is hardware. This is also comment from which city you're hearing this from. This script uses peer-reviewed sources from Nature, October 25th, 2025, detailing Google's verifiable quantum advantage achievement with 13,000 times speedup, and from China Daily, April 7th, 2025, reporting Origin Wukong's world-first billion-parameter AI model fine-tuning using quantum superposition and entanglement in Hefei. These are not secondary reports, primary sources, lab data. Now back to the information. In 2024, commercial quantum computer sales hit $854 million. up 70% from 2023. Not research grants, actual computer sales, systems installed, running workloads. First quarter of 2025 alone, 3 months. Investors poured $1.25 billion into quantum hardware, another $250 million into quantum software. Quantum Insider tracked the numbers. Market intelligence firm, they compile funding rounds, acquisition prices, government contracts, investment trends, not speculation, transaction data. Quantinuum raised $800 million in their latest funding round. Total raised exceeds that. Valuation hit $10 billion. Fidelity Investments joined. Fidelity manages $4.5 trillion in assets. They do not gamble. They analyze. Model, stress test, then invest. Fidelity sees quantum computing as infrastructure, like cloud computing was in 2005. Early, but inevitable. Quantinuum formed from the merger of Honeywell Quantum Solutions and Cambridge Quantum Computing in 2021. Trapped ion quantum computers, different technology than superconducting. Ions held in electromagnetic traps, manipulated with lasers, long coherence times, high gate fidelities, low error rates. The Helios quantum computer reached quantum volume of 65,536 in March 2024. Quantum volume is a benchmark. Combines qubit count, gate errors, connectivity, crosstalk. Single number. Higher is better. 65,536 is the record. Classical simulation becomes impractical. Quantinuum partnered with NVIDIA in 2025, NVQLink. Connecting quantum processors to classical GPUs. Hybrid computing. Quantum handles specific subroutines. Classical handles the rest. NVIDIA brings AI accelerators. CUDA ecosystem. Developer tools. Quantinuum brings quantum. Together, they target generative AI applications, training large language models with quantum subroutines, optimization loops, sampling distributions, tasks where quantum advantage is proven. Helios platform available through Quantinuum cloud services, also on-premises installations, enterprises with security requirements, financial institutions, government agencies, pharmaceutical companies. They want quantum computers inside their data centers. Behind firewalls, not in shared cloud. Quantinuum delivers both. September 2025, PsiQuantum became the world's most funded quantum startup. Raised $1 billion in a single round. $1 billion. That is rare air. Valuation reached $7 billion. Investors include BlackRock, Bailey Gifford, M12, Microsoft's venture fund, serious backers. PsiQuantum takes a different approach. Photonic qubits, photons as qubits, room temperature operation, no cryogenics, no dilution refrigerators, no 15 millikelvin cooling, standard telecom components, silicon photonics. Fabrication in existing semiconductor fabs. Global Foundries partnership. The architecture uses fusion-based quantum computing. Photons interfere at beam splitters. Measurements create entanglement. Error correction through redundancy and encoding. Fault tolerance from the start. PsiQuantum targets 1 million qubits, not 100, not 1,000. 1 million. Projected delivery by 2030, 5 years. Ambitious. But the funding backs the timeline. 1 billion buys a lot of dilution refrigerators, or in their case, a lot of photonic chip fabrication. According to SpinQ Research, quantum computing companies raised $3.77 billion in equity funding during the first 9 months of 2025, nearly triple the $1.3 billion raised in all of 2024. 3 times growth, year over year, acceleration. National governments are not standing still. They see quantum as strategic. Whoever leads quantum computing leads the next economy, leads AI, leads drug discovery, leads materials, science, leads cryptography, national security implications, economic implications. China invested over $15 billion in quantum research through 2025. State-backed initiatives, universities, national laboratories, Origin Quantum and Hefei. Major player, launched Wukong quantum computer, achieved world-first billion-parameter AI fine-tuning. United States countered with the National Quantum Initiative, reauthorized and expanded in 2023. DARPA programs, Department of Energy funding, National Science Foundation grants. November 6th, 2025. DARPA announced the next stage of quantum benchmarking initiative, selected 11 quantum computing firms, up to $15 million each. Total $165 million. Goal is utility scale computing by 2033. DARPA does not fund science experiments. DARPA funds technology with military applications, secure communications, code breaking, optimization, sensing, navigation, simulation. They want quantum computers that work in the field, not just in labs. European Union launched Quantum Flagship Program, €1 billion budget over 10 years. Started 2018. Midway through, over 5,000 researchers, 150 projects, academic institutions, startups, multinational corporations, Focus areas include quantum communication, quantum computing, quantum sensing, quantum simulation. Europe bets on photonics, Germany, France, Netherlands, strong optics industries, fiber networks, integration with existing telecom infrastructure. Japan ramped investment through MEX-T and JST, Ministry of Education, Culture, Sports, Science, and Technology, Japan Science and Technology Agency. Focus on superconducting qubits and quantum annealing, partnerships with IBM and Google, building domestic capabilities, training workforce, quantum literacy programs in universities. IonQ valuation hit nearly $19 billion by late 2025. Trapped ion quantum computers. Public company, ticker symbol IonQ. Listed on New York Stock Exchange via SPAC merger in 2021. Stock price volatility, but overall upward trend. Market capitalization reflects investor confidence. Real money at stake. IonQ deployed systems at universities, national labs, enterprises. Their Forte quantum computer features 32 algorithmic qubits, dynamically reconfigurable architecture, any-to-any connectivity. All qubits can interact with all others, not limited to nearest neighbors like superconducting grids, enables efficient circuit compilation, fewer gates, lower errors. The United Nations declared 2025 the International Year of Quantum Science and Technology. Mid-2024 announcement, global recognition, not niche anymore, mainstream. Yuval Boger, Chief Commercial Officer at Cura Computing, said significant financings reflect investor confidence in near-term commercialization milestones. Vendors, customers, and funding agencies treat quantum as entering deployment phase, not purely R&D. McKinsey projected industry worth $28 billion to $72 billion by 2035, from $750 million in 2024. 40 to 96 times growth in 11 years. Some see it hitting $99 billion by 2035. Broader market projections. Quantum technology market valued at $1.32 billion in 2024. Projected $9.65 billion by 2034, 22% compound annual growth rate, conservative. Real growth could exceed, commercial value is emerging. HSBC used IBM Heron in September 2024. Bond trading predictions improved 34%, quantifiable, not theoretical. Banks care about 34%. Industries are deploying fluid dynamics, finance, biomedicine, optimization, machine learning, natural sciences. IBM Quantum Nighthawk expected to deliver quantum advantage by end of 2026. The point where quantum solves a problem better than all classical methods. Timeline shrinking, advantage arriving, investment follows results, results justify investment. Positive feedback loop. Quantum winter is not coming, quantum spring is here. Speed multiplies 13,000 times. Billions pour in, each breakthrough enables the next. Willow's error correction makes quantum echoes possible. Quantum echoes proves advantage. Advantage attracts investment. Investment builds hardware. Hardware trains AI. AI discovers new quantum protocols. Pythias, finding simpler entanglement. Neural networks detecting entanglement dynamics. Quantum tunneling, replicating human perception. This is not linear progress. This is exponential convergence. Classical computing took decades to mature. Transistor invented, 1947. Integrated circuit, 1958. Microprocessor, 1971. Personal computer, 1977. Internet mainstream, 1995. Smartphone 2007, 60 years from transistor to iPhone. Quantum is moving faster. First quantum computer, 1998, 2 qubits. UC Berkeley, MIT, Los Alamos. Today we have systems over 1,000 qubits. IBM Condor, 1,121, Harvard 3,000 plus. 26 years from 2 qubits to thousands. The gap is closing. Fault tolerance achieved. Error correction below threshold. Real-time decoding. Logical qubits operating. Applications delivering value. Molecular rulers, AI training. Network simplification. The timeline for quantum advantage is not 2030, it is 2026. IBM Nighthawk shipping. Google, continuing Willow. Origin Wukong running tasks. PsiQuantum building million qubit systems. Target 2030. Commercial delivery. Artificial general intelligence was a dream 5 years ago. Now large language models with hundreds of billions of parameters converse like humans. Generate code, write essays. Analyze images. GPT-4, Claude. Gemini, they exist. Quantum AI will not replace them. It will transcend them. Models that explore parameter spaces through superposition. Entangled weights, capturing joint feature relationships. Classical networks cannot represent. Training 50 times faster. Using quantum tunneling to escape local minima. Achieving global optimization. Processing data streams with exponentially less memory. Quantum compression. Superposition over configurations. Decisions postponed until more information arrives. These are not science fiction capabilities. These are published results, peer-reviewed, reproduced, available. Your smartphone runs on quantum mechanics, transistors, LEDs, camera sensors, all quantum devices. You carry quantum technology. You do not think about it. Same will happen with quantum AI. Invisible? Ubiquitous, essential. Medical diagnosis, financial modeling, drug discovery, materials design, climate simulation, logistics optimization, autonomous systems. Every field transformed. The question is not if, the question is when. And the answer is your lifetime, probably your next decade. Some of you will build it, some will invest, some will use it, all will see it. There's one final thing nobody talks about. Late reveal, November 12th, 2025. IBM demonstrated real-time quantum error correction decoding in under 480 nanoseconds, faster than the quantum gate operations. You can correct errors faster than they occur. This is not just below threshold. This is active healing, quantum computers that repair themselves while running, no pausing, no restarting, continuous operation. That changes everything. You can run algorithms indefinitely, limited only by energy and cooling, not by coherence time. The billion gate milestone becomes achievable. Trillion gate algorithms conceivable. Simulations of systems with millions of interacting particles. Climate models with molecular resolution. Drug candidates tested in silico with atomic precision. Artificial general intelligence trained on quantum hardware with superhuman perception. Human-level reasoning, beyond human optimization. Conscious machines seeing optical illusions like we do, recognizing deepfakes, understanding art, processing reality, not in some distant future. In labs today, shipping next year, scaling this decade. The quantum AI era is not coming. It is here. Atoms entangled, photons indistinguishable, qubits coherent, gates fidelity above 99%, errors corrected in real time, algorithms verified, molecules measured, models trained. Billions invested, 7 breakthroughs, 7 reasons, 7 secrets, superhuman AI, your lifetime.